Welcome to Math341, Lecture 30. I'm Professor Miller. It's been a week. It is always hard coming back after Thanksgiving, so I thought this would be a really good time to do the Monte Carlo lecture. So we began the lecture with a couple of students being brave enough to try to throw darts at a piece of paper. This is related to integration. Okay? What is the big lesson I want you to learn from Calc 2?
You can't integrate.
You can't integrate. It is extremely hard to give you functions that are integrable with a nice closed form. And this is in one dimension. It gets worse when you get into higher dimensions. Well, if you're doing finance or a lot of applications of probability, you have to calculate these multidimensional integrals. And these become exceptionally challenging to do. And so what I want to do today, am I vaguely in range?
C.
Muchas gracias, señor. Monte-Carlo integration. Out of curiosity, how many people have seen Monte Carlo integration before? Excellent. The cell phone policy is on hold today, so if your phone rings, there's no penalty. My son is homesick, and so just in case anything is happening, I need to be able to hear. Okay, so the idea is the following. We want to calculate areas or volumes or hypervolumes or whatever, and we can't integrate. Given that we can't integrate and we need to integrate, this is not a good start. So we need to find a way to calculate these quantities without doing integration. And again, just because you can write down a formula, just because you can write an expression, does not mean you can do it. You know, I want the integral from 0 to infinity of r to the square root of the cosine cubed of the sine of r times e to the r cubed plus the square root of r dr. Okay? And well, let's make it to a negative so at least it converges. I can write this down, and I have absolutely no idea how to calculate this. I can estimate it, but I can't calculate it in closed form. All right. So the idea of Monte Carlo integration is the following. Let's assume we have a unit square. It doesn't have to be, yes?
How would you go about estimating that?
I would basically just break it up into lots of intervals, and on each interval I would do like a trapezoid. So if I give you a function, you know, the trapezoid method is a really good method to estimate the area. There are other things you can do as well. There's Simpson's formula. There's lots of different things you can do to calculate areas under curves and estimate them. But for something nasty like that, you are not getting a closed form solution. Sometimes in things like that that look terrible, it's actually possible to write down the answer because it's from 0 to infinity. And sometimes there's nice ways of doing it. For instance, the integral from 0 to infinity of e to the negative r squared dr, there actually is a nice answer for that. And it involves the square root of pi. It's the normalization constant or close to it of the Gaussian. In situations like that, we sometimes have nice answers if it's a complete integral. For a partial integral of this from like 1 to 5, no. All right. So let's imagine we have a unit square. And let's imagine we have two curves. I'll say u of x for upper and L of x for lower. And I want the region between them. Well, I would, if this is A, and this is B, and this is 0, and this is 1, the area is the integral from A to B of u of x minus L of x dx. But we can't evaluate that. What do you think might be useful to calculate or to at least estimate the area? Do you see anything that looks like a unit square anywhere in this class?
Outcome space?
I'm sorry?
Outcome space?
No. There is something in this classroom right now that looks like a unit square, other than this one right here. Yes?
Probability.
Not probability.
Piece of paper.
Yeah, this piece of paper over here where I was having you all throw dots. Right? Some of you even on the dartboard. Okay, let's look at the piece of paper. Beautiful picture on the back of papers like this, with like a bow and boundary curve. I'm throwing darts at this piece of paper, and I'm asking how many of the darts land inside the region, and how many don't. Or equivalently, what fraction lands inside the region. This becomes a way to estimate areas, or volumes, or whatever. Imagine we have a situation where it's easy to tell, are you inside or outside? So xk will equal 1 if dot k lands inside region and 0 otherwise. Yes?
Isn't that a little biased though because we're aiming for the center?
I did not tell you to aim for the center. I told you to throw uniformly on the piece of paper. So you're absolutely correct that if you are throwing towards the center, or if you are choosing the points with some kind of bias, that will affect the method. And you can take that into account in terms of estimating your true area if you know the bias of the thrower. Okay, am I still in focus?
Agreed.
Okay, even better than being in focus, thank you. So what's the probability that xk equals 1? Yes.
Is that just the area over
Yeah.
1?
It's the area of the region. And I do like how you said divided by 1. Now, does it really matter if you divide something by 1? No. But if this was not a unit square, if this was a 2 by 3 rectangle, then I would divide by 6. And so if we can throw points uniformly, we can use that to calculate the area. And each xk is going to be a binary indicator random variable. And our tosses will be independent, and they'll be identically distributed. What theorem do you think is going to become useful? Yes? Yeah, the central limit theorem. Right? This is why I'm wearing the hat again today. This is going to be one of the best applications of the central limit theorem. As you throw more and more dots, do you expect to have a better and better estimate or a worse estimate? Better. It is possible that you could get a worse estimate. But, according to the laws of probability, the more times you do this, the better it should be. And now we can ask about how good of an estimate do we expect it to be. So we start throwing dots and we start getting points, and some of the points are inside and some of the points are outside. And we look and see what fraction of the points land inside the figure. Do you think that choosing a uniform distribution on throws is the best way to attack this problem? As opposed to deliberately, say, targeting the center. If you want to get an estimate that's accurate for this region, do you think I should be deliberately trying to throw in the center, or I should be trying to throw uniformly on the square? Uniformly on the square. And yes?
So I'm thinking about this, and like we had Josh come talk to us.
Yes.
And with him, he has like billions of dots.
Correct.
Just everywhere. For him, wouldn't he be putting the piece of paper down on the dots? Because he's looking at something that's already established. He has data points already there. And we're saying we're throwing darts on the paper. So wouldn't it be a different perspective in terms of an application?
What are the data points you're talking about for him?
So people that subscribe, unsubscribe, people that are there for more than 6 months, less than 6 months.
All right, so this is what I was talking about that Kim might be calling. So. So it's a different thing. He's looking at those data points and trying to detect patterns, trying to detect what are good indicators of future behavior. So what I'm trying to do here is I'm trying to estimate what's the area of a region. So it's a slightly different problem. There's a lot of simulations that you'll do, but
So what if he says that the sweet spot, the people that are most likely to subscribe, the people that will give us the most money is like this?
that's a
region
different
here?
question. That's you're trying to find the best value of a parameter for certain behavior. I'm trying to find what's the area of this.
Okay.
Maybe anybody who is in this region will become a subscriber. And I want to figure out what fraction of the space is a subscriber if people are uniformly distributed. If people are not uniformly distributed in the space, if there's a bias in the space, you can actually take that into account and then trying to estimate maybe what this area is. If we want to choose points uniformly in a unit square, that's not so bad. We can choose the x-coordinate uniformly, the y-coordinate uniformly, and then put them together, and that will give me a uniform dot. The question is the best way to estimate this area to choose points uniformly and throw them? So here's what often happens. You have a very complicated problem, and you can allow the computers to run for a certain amount of time, and then you need the answer to give your boss. So years ago, I worked on a project for some movie distributors, and we had 2 hours from when we got the list of candidate movies to when we had to determine the optimal schedule. And the problem was so complex, 2 hours is not enough time to solve it. So we did the best we could in 2 hours, and we went with that. So imagine you have a fixed amount of computational time. Maybe you can throw 100 data points. Instead of throwing the data points randomly, what might you do if you have 100 data points? Yeah.
Arrange the data points in a lattice.
Yeah, maybe do like a 10 by 10 lattice.
Yeah.
Because that will guarantee that you sample uniformly in the space. Whereas if you throw randomly, you're going to have clusters of points where you miss, and you will have clusters of places that you oversample. So this then comes down to the theory, if I have a bunch of random points, what kind of clustering effects do I expect to have? If I know that I have enough time to do 100 observations, I'll choose a 10 by 10 lattice. That will spread things out. Yes?
What's the value in doing a 10 by 10 rather than just what we have now?
Because if I do it like this, there will be places where the dots will you'll have more dots than you should. And you'll have places where you have fewer dots than you should. Just because of uniform minimum variables. If you throw a bunch of points uniformly on the square, if you throw 100 of them, you're not going to get all parts of the space equally sampled.
But do we care? I thought it was either you're in or you're out.
Right, but if I don't choose my points uniformly in the space, if there are some places that I oversample and some places that I undersample, depending on what my region looks like, I could get a bad estimate for the true area. And so imagine I have another small part like this that's hugging the corner. If I don't have anything in here, I will completely miss that. It's like playing the game Battleship. If you choose your points randomly, that's fine, but you will have clusters that you miss where you could have big enemy fleets missing.
Oh, I was going to say, is it at what number of darts does it become a better strategy to throw randomly than to make a lattice?
Well, a lot of it is if you know exactly how much computational time you need, a lattice is terrific. But imagine you miscalculated. Imagine you thought you had time to run 100 observations, and you actually have time to run 107. So now you have 7 more to throw. The problem with 7 more to throw is you can't just extend the lattice. And you've already made those initial 100 observations. So now that you have 7 more, how do you do that? There's actually a way to put in what's called almost a quasi-lattice. And one of the best ones actually involves shifts of Fibonacci numbers, where you're just going through the space but like at an irrational angle. So as you keep going, you'll basically keep spreading out throughout it. So if you actually have more runtime, you just keep sampling. So what I want you to know is that there's an advanced theory that if you want to do better than just throwing the points uniformly, there are things you can do to minimize different types of errors. Now, the best thing you can do is, of course, just throw a lot of points. The more points you throw, law of probability kicks in, the more likely you are to get a few things in there. And your error will go down significantly. So if you know exactly how much computational time you have, you can build a lattice. If you want to allow yourself the opportunity of maybe doing a little bit more, if you have a little bit more computational time, you can do a quasi-lattice. For the purposes of today, we're going to just throw points randomly and explore what happens. Okay? So we're going to analyze the simplest case, and you have some idea of how you can make things better. Okay, so any questions on the setup? So what we want to do is we want to calculate the distribution of a prediction for the area. And we want to get some idea of what is our error. If I tell you that you're going to get a 75% on the final, plus or minus 80%, this is no useful information. Correct? You want a useful estimate. So when I'm doing something over here, how close do I think I am to the true area? Is it possible that I'm nowhere close? Absolutely. Maybe every single dot comes in the bottom left corner. It is unlikely for that to happen, but it's possible for it to happen. All right, so let's try to calculate. So we'll keep things in the unit square. Let's let yn be x1 plus xn. And what do you think I should study? Do you think I should study just their sum? Or do you think I should study something closely related to their sum? Any thoughts? So what would this sum represent? Yes?
Should we study that divided by n?
Yeah, I would study this divided by n. So yn should be approximately the area if n is large. Right? What's the expected value of yn? Well, the expected value of a sum is the sum of the expected values. Each one of these has the expected value area. I have n of them, and then I divide by n. So its expected value is the area. So if you've taken some advanced statistics classes, you might have heard about unbiased estimators. We like unbiased estimators. Sometimes if you know what the bias is, you can remove the bias, but it's nice that the expected value is the number we want. Okay, now let's calculate the variance of yn. So again, for the rest of the semester, I'm really not going to be introducing new mathematics. What we're going to be doing is we're going to be looking at the mathematics we've been doing all semester and seeing why we care about it. What can we do with it? Why do we spend so much time developing this theory? There are people who call the papers that led to this method the most influential papers of 20th century mathematics, in terms of just how many things we could not solve, but can now solve, or at least approximately solve, using estimates like this. One of the early applications of this was the Manhattan Project, in terms of trying to estimate, oh, I don't know, will this cause a nuclear explosion that goes out of control and actually destroys the entire world when we do our test? Or will it be a localized explosion, and is it safe to actually do this? You know, how far will the chain reaction go? There were a lot of estimates that needed to be done, and they were estimated using stuff like this. All right, anybody want to give me the variance? Yes?
So it's n times the variance of x and divided by n squared?
So the variance of a sum is the sum of the variances when they're independent. So we get n times the variance of the first one, and then we have to divide by n squared. So it's going to be the variance of x1 over n. Well, the variance of x1, we have a binomial random variable, not binomial, Bernoulli random variable, binary indicator variable. That's 1 with probability 0. So that's 1 with probability area and 0 with probability 1 minus area. So we know that for these Bernoulli random variables, the variance is p times 1 minus p. So it's going to be area times 1 minus area divided by n. Moreover, what should the distribution of yn look like? What do you think the distribution of yn should be converging to? normal. It's not centered because I'm not subtracting off the area. Why don't I just subtract off the area? I mean, then we could be converging to the standard normal. We'd like to converge to the standard normal. We don't know the area, right? If I knew the area, I wouldn't be doing all this. Or I would be doing this as a way to test what I'm doing and making sure that I understand things. I don't know the area. So this is one of the big applications of the central limit theorem. When you don't know the mean, well, just sample it many, many times, and this should become normally distributed, and the expected value should be the mean, and then the variance is decaying rapidly. So that means the standard deviation is area 1 minus area divided by n, and then take the square root of all that. So every time I increase the number of data points by 100, I get one more decimal digit. So that gives you some rough idea of how challenging the calculation is going to be. So what is going to be the hardest area to estimate well? Yeah, I mean, the variance will be largest when the area is a half. This is when basically the region and its complement are both of the same size. Okay. Any questions about the theory? It's actually amazing how straightforward the theory is. One of the early applications of this, I think, was to estimate the probability of winning, I think, some card games like solitaire. And the idea was, well, rather than trying to calculate theoretically what is the probability of winning, let's just simulate a bunch of games and see how often we win, and then just use that. So this is the idea we've been doing in all of the coding, or at least a lot of the coding throughout the semester. I want to calculate a very difficult probability. Let me run a simulation. Let me estimate it. Okay. So what I want to do now is I want to switch to doing some computer examples. And I just want to make sure. And this is why I'm being extremely careful, because it actually says what the region is, and I want to just make sure that you can't see that on the screen. That is why it was on mute, and I hadn't even had it plugged in. So I had extra chime. Okay. So I have thrown 2 points. Red is inside. Yes?
You need to recenter.
I'll do it later. Oh, the recorder? Okay, how far off is it?
No, 2 feet maybe.
Okay.
Well, I'm just saying it needs to move to the right a little bit. Yep.
Right. Now, the question is, I'm not sure. So hopefully this will work. Okay. So it's going to put red if you're inside the region, blue if you're outside the region, and it's going to keep a running tab of, I think, what the estimate of the area is. Okay? Any thoughts as to what the shape is? You really should not have much thoughts right now. So when you think you know what it is, shout it out. So it's adding more and more points. Any thoughts on what the region is?
And in the red is the region.
The red is the region.
Is it just going to be like a square?
So I've heard square, I've heard circle. So let's pause. if it's going to be a square, could it be a square? It could come down like this, over like this. Well, now these few blue points over here make me hesitant to say it's a square. These ones over here, it looks like it's, without those points, it looks like it would be, now a hexagon it could be. And again, this is why I want to slowly do something like this. It could be a hexagon. But remember, I'm lazy. I'm a math professor. I rather than have to write the program for a hexagon. How much harder is it to write a program for a hexagon versus a square or a circle? Circle's really easy.
Is it a circle?
It is a circle. But here's the other thing. We were talking about the issues between using a lattice and choosing points uniformly. These points are being chosen uniformly. Do you see clustering? Hell yes. A lot of clustering over here. A lot of clustering over here. Big gaps in through here. One of the things people do not understand is that with enough data, likely should happen. And if you had things that looked too uniform, I would know the data was fake. So let's run it. I'll speed up time a little bit more. I hope it's recording. It often does not record, but is it showing the dots at least? Oh, that's good. That's better than last year. All right. And now you can see a running tab. So here's the running tab of the area. Does that seem a reasonable area? 3.05.
How does it get the bound of the circle? Is it just the furthest point out?
Well, I am looking at the circle x squared plus y squared is less than or equal to 1. So if you choose a point uniformly in the unit square, well, I guess not the unit square, in the square from -1, -1 to 1, 1, if x squared plus y squared is less than or equal to 1, it colors it red and considers it inside, otherwise it considers it blue. What should the area be? Pi.
It's not very good, is it? Well, you have hundreds of points there.
135,000.
So, okay, we have 135.464 points.
Well, really?
Yes.
Isn't it more than that? The number of points is going up faster than that number.
It looks like there's more than 135.
Definitely more than 135.
That's interesting. So I will have to check and see how this is related.
Well, how could you have like 0.464?
Well, this is just for display purposes, because I have it with a parameter. I'm using the manipulate command in Mathematica, and so to play this, I'm just allowing things to roll, and it only bumps it up when it actually goes up to the next integer. So for instance, if I change this to 8 there, you won't see any change. But if I move it up to 136, a new point came in right in through here. So it's just for display purposes.
Could you put in like 5,000?
Yeah, so I mean, I'll let it run a little faster now. I'll go even faster.
What's the max on this for num2?
I'm not sure.
Oh wow.
All right, so whoops.
Like 10,000.
Oh, okay. So here I'm at 4,427 out of this 0.24 points. I'm now getting 3.109. That's about 3.11. If you look at what the square root of 4,400 is, that's not a horrible error. Again, if answers are too good, the data is almost surely cooked. You should have some idea of how good to expect. We talked about Buffon's needle earlier in the semester. There's a great experiment that somebody did where they threw the rods on the grid to calculate pi, and they got pi to, I think, 8 decimal places. And somebody noticed, it's amazing. If he had thrown one more rod, no matter how it landed, he would have gone down to 3 decimal places. The number of rods he threw was equal to a denominator in a really good rational approximation to pi. Again, you can't prove that the person cheated. But the number of rods thrown was exactly equal to the denominator of a really good rational approximation of pi. And it makes one highly suspicious. So when you see things that look too good to be true, be concerned, be aware. Are you seeing clustering here? Now, look at this big gap into here. We've got a lot of stuff into there. If I take small windows, I do not expect every small window to be uniformly distributed in terms of number of points. And this is one of the issues in choosing points like this. So if you're interested, I believe the additional comments have some stuff about these quasi-lattices and how you can use Fibonacci numbers. If not, email me. It's a wonderful, wonderful subject. But you can begin to see the challenges. Let me wind up a little bit more. I'll just go to the very end. All right. So this says using 8,000 data points, you got 3.129. Not bad. So here's a way to numerically approximate pi. You should not be able to see anything now, is that correct?
Correct.
Excellent. I want to switch to the next one. Okay, thoughts?
Square.
Square.
Rectangle.
Rectangle. .6, 1.45, 1.33. Any thoughts? Ellipse. So let's increase the speed. And again, you can see clustering. It's also interesting to look at where the dots are landing. And so we're at almost 1,000 points now. At this point, you can begin to see the outline of the ellipse pretty well. So here is 8,000. And I get 1.59. What's the area of the ellipse? So we'll do a little bit of theory for the last 10 minutes of class. But I will remark, you can definitely see regions of clusters. There's like a nice heart over there. There's some big deserts and gaps in through here. And this is something you need to be aware of. That these are lower order effects. I mean, the main is pretty close. But as a nice exercise, read up on quasi-lattice. I'll make this an extra credit project. And actually write a computer program to simulate, using a quasi-lattice, the area of an ellipse or the area of a circle.
Half of pi, right?
I'm sorry?
Half of pi?
For this problem, yes. So if you have an ellipse where the semi-major axis is A and the semi-minor is B, what's the area of the ellipse? Pi AB. So the question is, why is it pi AB? We don't have a button to push to raise the screen. So let's just do a little bit of theory. How many of you calculated the area of an ellipse in multivariable calculus? Okay. Now, when you look at ellipses, I believe you always look at ellipses that are aligned with the major axis. And this is A, this is minus A, this is B, no, minus B, this is B, and it's x over A squared plus y over B squared equals 1. How many of you have ever done ellipses that are not aligned with the major axes? What if I give you an ellipse like this? Do you know what the formula is in that case?
Do you have to use a triangle to figure it out?
No. Linear algebra. So this becomes an opportunity to talk about linear algebra. If I had to distill a huge amount of linear algebra into one sentence, it's finding the right perspective for the problem. What coordinate system is best? I am from Boston. For the most part, I do not like New York City, but I have to admit one part of New York City does something much better than Boston. Which part of New York City and what is it? The grid system. Yes. If you had said something related to baseball, you could have failed the course at that moment. Let's draw new axes like this. We'll call this the UV space. And here's the initial XY space. Well, we know what the equation of the ellipse is in the UV space. space, it's actually UV 1 over A squared, 0, 0, 1 over B squared, UV equals 1. That's how you write the equation. Is this all in focus? Okay. Okay. So if we write it like this, this is a nice way to write the equation of an ellipse in matrix form. It's basically your point times your matrix times your point is equal to 1. Actually, this is the transpose of the point. If I had a hyperbola, I would just put a negative 1 over b squared here. And how do I get from xy to uv? I just rotate by theta. So uv is some rotation matrix of theta times xy. And this matrix, it's like cosine theta, sine theta, sine theta, cosine theta. One of them has a negative sign. If I take the point 0, 1, that's got to go to a negative value, which is 0, 1. I think the negative sign. The mathematicians and the physicists do things slightly differently. One of us rotates the axes, the other one rotates the point. Because I've taken both, I no longer remember which one is which. But I think it's something like this. And now you would get your equation. UV is r theta, so you would get basically xy r theta transpose 1 over a squared, 0, 0, 1 over b squared r theta xy equals 1. And then when you expand this out, you would get something x squared plus something xy plus something y squared equals 1. And this will give you the equation of an ellipse centered at the origin. If it wasn't centered at the origin, then you would have to have a translation component as well. But again, this gives me an opportunity to highlight one of the great insights from linear algebra. Choosing the right axes, choosing the right orientation. We know how to solve the equation of the ellipse when it's aligned with the coordinate axes. So just lean back. And if you lean back, you know how to do it. So what you do is you change your coordinate system, solve it in the nice basis, and then change back. And that's essentially what goes on here. We change, solve, change back. All right. Let's talk about calculating the area of the ellipse. It turns out the area of the ellipse, or the more general case if we had plus z over c squared, if we had the ellipsoid, the volume of the ellipsoid, these are actually very easy to do. If you want to calculate the perimeter of the ellipse, this is actually a very difficult problem. The only solution we have is to use infinite series. And I was reviewing a calculus book that had an explicit, nice closed form expression for the perimeter of the ellipse, and I knew that the authors had some issues. All right. Let's calculate the area. So it's the integral x over a squared plus y over b squared is less equal to 1 of dx dy. That's the area of the ellipse. I'm going to change coordinates. What should I let u equal? What should I let v equal? U and v should somehow be related to x and y. What would be a good choice for u? What object is very similar to an ellipse? A circle. A circle is an ellipse where both directions are the same. So what relationship should I have between x and u? U should be x over a. And that will imply that dx is a du. V should be y over b, which implies dy is going to be b dv. How many of you remember at least hearing about the change of variable formula in multivariable calculus? Right? Where you have the Jacobian and you have how the volume elements change. We're basically going to bypass all of this. I don't like to actually integrate. This is the same as integrating over u squared plus v squared less than equal to 1. And now what does dx dy become? Yeah. A, B, du, dv. The Jacobi is really nice in this change of variable. I'm basically just rescaling the x, I'm rescaling the y. Okay, well this is the same as AB times the integral u squared plus v squared less than or equal to 1 du dv. Oh, well, what's the area of du dv when u squared plus v squared is less than or equal to 1? Pi. Because that's a circle of radius 1. And there's your formula for the area of the ellipse. And as a check, if A equals B equals I, yes, you get pi r squared. Question? Or? Okay. Yes?
To get the parameter, can we just take a derivative?
To get the what?
Take the
No.
Why not?
Let me make sure there's no questions on this, and then I will open up that hat. That is a painful question. So any questions about this? So what's nice is looking at the formula, we go back and we revisit the experiment we did where it was conjectured that it should be 1/2 pi. And in the case we did A equals 1, B equals 1/2. You could actually check lots of different values of A and B and see what answers you get numerically and try to sniff out the relationship. So, any questions on this? All right. So I will answer your question by doing a little bit more than what you asked. I'm going to prove that any two curves that connect the 2 points have the same length so long as they are always moving in the direction from one point to another.
Can you say that again?
Yep. So I'm going to take any 2 points, and I can take any path from one to another, and they all the paths have the same length. As long as I don't do something stupid like going backwards and spiraling like that. Any 2 paths have the same length. Some of you look skeptical. All right. Let's look at the straight line path. All I have to do is prove every path has the same length as the straight line path. I'm going to approximate the straight line path by a very, very, very small ladder. And by continuity, there's really not much difference. And so I can replace one with the other. Well, what's the length of this ladder path? Well, all the horizontal segments drop down. All the vertical segments push over to the right. And you've now just shown that the 2 sides of a right triangle add up to the hypotenuse. So while you are locally close, that does not mean you can replace this length with something like that. For calculus, it's not ds is dx plus dy, where ds is like an infinitesimal arc length. It's ds is the square root of dx squared plus dy squared. And that's why perimeter is such a pain to deal with. And that's why areas are so much nicer, or volumes are so much nicer. Because the small little thing like this, well, if I'm going for an area, that's not going to matter. The area that I'm missing is negligible. All right. So I think this is a good place to stop.